Hello everyone. Today we are going to study atomic size and its trend along the modern periodic table. As on the left-hand side, you can notice that not all elements have their atomic size same. There is a huge difference when we look along a period and along a group in the modern periodic table for the size of the element. We are going to study the reason what causes this particular difference, and we are going to study whether there is a trend or whether there is a pattern that we can affirm to. First of all, let's try to understand what is atomic size or atomic radius. Okay, so I have presented two atoms over here. Okay, you can take up any atom of your choice. There's no such difference. Now, what happens in these atoms? The last shell or the last orbit is called as the valence orbit. Okay. This particular valence orbit, this particular valence orbit is very important. Why? Because this is going to help us determine what is the atomic size. In layman's language, atomic size is nothing but the distance from nucleus to valence shell. What does that indicate? That the central region or the nucleus to the last orbit, whatever is the distance, that asserts to atomic size. We calculate atomic size in PM, that is picometer. Okay. Now, the actual definition, according to many textual books, is this. The atomic radius of an atom can be defined as 1/2 of the distance between the two nuclei in a diatomic molecule. More or less, it's the same concept, just that they are considering, let's say that there is one atom over here and there is another atom over here. They are saying that atomic radii is what? You take the distance from one nucleus to the other nucleus in a molecule. Okay, and this becomes what? This is called as the distance d. Then you divide d by 2. So you get what? The distance between the nucleus and the valence shell of the first atom. More or less, the definition is same, just that the textual definition is a more prominent one, so you need to understand the meaning of it. Okay, so let's understand what influences atomic size. What are the factors affecting atomic size? There are two main factors which I teach every time. First one is number of valence electron, meaning electrons in the last shell. And second one is number of shells, meaning how many orbits are there in that atom. For this, let's consider an example. In the modern periodic table, the third period, okay, has got such elements. I'll just show you the period if you want. Third period is 1, 2, 3. There's sodium, magnesium, aluminum, silicon. This is the third period. And we are considering the first group, lithium, sodium, potassium, rubidium. So I'm going to consider one period and one group for you to understand. Period 3 has got sodium, magnesium, okay? And group 1 has got sodium and potassium, okay? Now, in this particular period 3, sodium has got atomic radius of 186 picometer, whereas magnesium is 160 picometer. In the group, sodium has atomic radii of 186. Potassium has a 227 atomic radii. How are they arranged actually? Let's see. So you have something like this. Group number 3, you have sodium and magnesium. So technique period number 3, there is sodium and magnesium, same period. And then group number 1, sodium and potassium. So one is going top to bottom. Period is growing left to right. Okay. Sodium has got an atomic size of 186 picometer. Magnesium has got an atomic size of 160. Potassium has got an atomic size of 227. our understanding is what is influencing this parameter of atomic size, that when we look across a period, 186 to 60, atomic size is decreasing along a period. When we look across a group, 186 and 227, atomic size is increasing down a group. So what is the major reason influencing that? That we are going to understand in this particular lecture. Okay, so let's see the reason. Generally, I teach it with two parameters over here again. First, we are going to understand the reason with respect to effective nuclear charge. And second would be with respect to electron shielding effect. Names might look tough, but believe me, once you understand, it's an easy concept. So let me simplify that for you. Let's understand effective nuclear charge first. What is effective nuclear charge in layman language? Pull experienced by valence electrons. Now, electrons are negative, right? Towards the nucleus, which is positive. Nucleus has what? Proton. Proton is positive. So this positive proton in the nucleus is going to pull the negative electron towards itself. That is the logic. Okay. So valence electron is being pulled by the nucleus. So how much ever is the pull, that is called as effective nuclear charge. So let's say there are three atoms, A, B, and C. Pay attention over here. All these three atoms that I've taken, all of them have two shells each. What is different? The valence electron. A atom has only one valence electron. B has two valence electrons. C has three valence electrons. Now look at A. Effective nuclear charge is pull experienced by valence electron or electrons towards the nucleus. So this one particular electron is being pulled towards the nucleus in A. In B, there are two individual electrons pulled towards the nucleus, right? And in C, there are three individual electrons being pulled towards the nucleus. It's as good as looking that while pulling one electron, okay, let's say, let us annotate it this way. Okay, it is taking only one EMC. Okay, minimum EMC. Okay, minimum pull is required because only one electron has to be pulled. When two different electrons are pulled, just imagine there needs to be an extra pulling effect. Yes or no? You are pulling two different electrons. So there was one electron already being pulled. Now another one is also being pulled. Because of this pulling of electrons towards the nucleus, there is a shrinkage in the atomic radii. See over here, while we are talking about C, we have 3 ENC over here. 3 ENC meaning 2 electrons are being pulled individually. Now third electron has been added. Now when you add this third electron in the valence shell, what is happening? The nucleus needs to pull that itself, right? So every individual valence electron is experiencing a pull towards the nucleus. So as the valence electrons are increasing, the pull towards the nucleus is also increasing. And that decreases the atomic size. Meaning, with each adding electron on the valence orbit, your atomic size is going to decrease. Let's try to have a look, okay, whether what I'm telling is correct or not. Okay, now when we go along a period, see sodium to chlorine. Sodium, you might know, has an atomic number of 11, right? So its configuration is 2, 8, 1. Chlorine, on the other hand, has an atomic number of 17, 2, 8, 7. See, only one electron needs to be pulled in sodium, whereas 7 individual electrons need to be pulled in chlorine. That also affects the atomic size. So as the valence number of electron is increasing, we can see a decrease in the atomic radii. That's why atomic size of sodium is 186. Chlorine's atomic size is 99. We'll be discussing the examples in detail. This is just for you to understand prior. Okay. That was effective nuclear charge, correct? Let's see ESE. ESE is what? Electron shielding effect. What is electron shielding effect? In layman language, electron shielding effect means the inner electrons are electrons shield the outer electrons from experiencing a nuclear pull. What does this mean? For this, we'll take an example. A, B, and C. We have three atoms over here. First atom has got two shells. Second one has got B atom has got three shells. C atom has got four shells. Okay. Now in this, we need to know one thing, that whenever we write the configuration, these are nothing but orbits, right? K, K, L, M, N, meaning what? The first orbit, second orbit, third orbit, fourth orbit, right? So the first orbit can hold only 2 electrons. By default, when we are talking about practical nature, second can hold 8, third can hold 8. Okay. Now, what is happening over here? Let's try to understand. The first orbit in A atom is holding 2 electrons. In B, first orbit is holding 2 electrons, second orbit is holding 8 electrons. In C, first is holding 2, second orbit is holding 8, third orbit is also holding 8. What does this mean? That nucleus can easily attract the valence electron of A. See, in all these three, A, B, and C, valence electron number is same. Only one electron in the valence shell, meaning that ENC is not creating a problem. What is creating a problem? The barrier which is coming in between. So in A atom, we have only two shells. So only two electrons in the first shell are obstructing the valence electron. In B, there are 10 electrons before the valence shell who are going to shield the valence electron from experiencing any pull. In C, there are 18 electrons before the valence shell who are going to shield the valence electron. So if you notice, slowly and steadily, because the inner shielding is increasing, inner number of electrons are increasing, the valence shell and the valence electron are going farther away from the nucleus. The more far, or we can say farther away, a particular valence electron is from the nucleus, less would be the pull experienced by that electron, because many members have come in between. They are going to shield that last electron from getting pulled towards the nucleus. That's why as inner electrons increase, the shielding effect also increases. That is the reason why atomic size increases. And where do we see number of shells increasing? We see it along a group, right? Let's try to understand these with an example. In period 3, we have sodium and magnesium. Sodium has been given an atomic size of 186, magnesium is 160. So you can see along a period, that is when we move from left to right, along a period, atomic size tends to decrease. Why is it decreasing? See over here. Sodium has an atomic number of 11, magnesium has 12. Sodium's configuration would be 2, 8, 1. Magnesium would be 2, 8, 2, right? In sodium, only one valence electron is present, whereas in magnesium, two valence electrons are present, meaning sodium's nucleus only needs to pull one electron, but magnesium's nucleus needs to pull two individual electrons towards itself. So what is that we have learned? As number of valence electrons increases, the pull or the ENC also increases. And as ENC increases, atomic size decreases a longer period. Okay, the more pull is observed towards the nucleus, that much atomic shrinkage would be observed. Okay, so whenever you see that ENC is high, you will always find that the atomic size is small. Wherever the ENC is low, atomic size would be bigger. Okay, that was a longer period. Let's see a longer group. When we are looking along a group, we have sodium first, and below sodium, we have potassium. So along a group, we are moving from top to bottom. Here we can check sodium's atomic size is 186, whereas potassium, which is just beneath the sodium in the periodic group, it's 227, meaning it has increased. So what is causing the increase in atomic size as we go down the group? Logic again is the same. Look over here. Sodium has got configuration 2, 8, 1. Potassium has a configuration 2, 8, 8, 1. Meaning sodium and potassium both have one valence electron. But what is changing? What is different? That needs to be highlighted. Sodium has only 3 shells. Potassium has 4 shells, meaning sodium's valence electron is shielded by only 10 electrons prior to it. But potassium's one valence electron is shielded by 18 electrons. Here, what will come into effect? Here, the best form that we can think of is inner electron shielding. So when the number of inner electrons increase, the shielding effect also increases. And whenever there is shielding, there is less pull. As a result, atomic size increases along a group. So by now, you must have understood when valence electrons are changing and the shell number is same, we use ESE. When shell numbers are changing and valence electrons are same, it would be better to use ESE. Okay, let's see over here. Along a period, number of valence electrons increase, ENC increases, atomic size decreases. Along a group, number of shells increases, number of valence electrons are not being considered over here, only shells. So number of inner electrons increase and that increases the shielding effect. So how can we balance this out? We can take a small gesture out of it. Okay, so ENC, what is happening? It is inversely proportional to the atomic size. So whenever there is more ENC, the atomic size is bound to be smaller. Whenever there is less ENC, meaning valence electrons are less, pull is experienced less, that time the atomic size would be bigger. ESE, on the other hand, is directly proportional to atomic size, meaning more inner electrons are going to be present, more would be the atomic size. Less inner electrons, less number of shells, smaller would be the atomic size. Okay, I hope with this you might have understood what we are trying to get to in this particular topic. Okay, so for that, we can take 1 minute and look over here. Along a group when we are seeing, see, lithium was 152. Last element before the radioactive element, we have got a cesium, 265. You can see an increase in atomic size along in group. Okay, it's because of the increasing number of shell that is going to increase the ESE and increase the atomic size. Along a period, you can check lithium 152, fluorine 72, sodium 186, chlorine 99, potassium 227, bromine 114. What is happening along a period? Along a period, the number of valence electrons are increasing. That's why ENC or the pull is also increasing. That's the reason why atomic size is shrinking along a period. With this, we stop. Next lecture, we'll meet with ionization enthalpy. Till then, signing off. Bye.